So here is a 10-question review for exam number 3. And this includes the chapters of static equilibrium, rotational motion, angular momentum, and fluids. So in the first question that we're going to look at, the concept of center of gravity needs to be understood. The center of gravity is the point through which the weight of any object is imagined to act. So if an object is suspended exactly at its center of gravity, then it will be completely balanced. That means the torques on both the sides will be equal. So here is the first question. So in this question, we have the center of gravity of the meter stick. Usually, it is at 50 centimeters, but it need not be. And in this case, the center of gravity of a meter stick is at the 49.0 centimeter mark. And we have a mass of 40.0 gram, which is placed at the 90 centimeter. And then the stick balances at the 62.0 centimeter mark. What is the mass of the meter stick? So that is the question. So where is the pivot in this question? The pivot is at 62.0 centimeter because that's where it's balanced. And you only have one mass, which is 40.0 gram, placed at the 90 centimeter mark. So how is it balancing? So that is the 62.0 centimeter mark, and then the pivot is right there, and then you have a mass at the 90.0 centimeter mark. How much is that? It's 40.0. And so what is balancing it is actually the mass of the meter stick acting through this point, which is, we know, at 49.0 centimeters. So that's where the mass of the meter stick is acting. So when you take the torque about the 68 centimeter, there are two torques. One is the clockwise torque due to 40 grams, and that would be 40 times this distance. 40 times 90 minus 68, which should be equal to the counterclockwise torque, which is given by m times this distance, which is 68.0 minus 49.0 centimeter. So in static equilibrium, the total clockwise torque must be exactly equal to the total counterclockwise torque. So there it is. Just what I told you now. Torque is force multiplied by the perpendicular distance, but in this case we're taking the mass because the g cancels out on both sides. And then when we do the math, on the left side you get m times 13.0, and on the right side it's 40.0 times 28. Calculations give the mass of the meter stick as 86.2 grams. That's the first one. Now on to the second one. In the second one, again, it's dealing with static equilibrium. So I'm going to list the conditions for static equilibrium. There are two conditions for static equilibrium. Number one, the total forces acting up should be equal to the total forces acting down. Or in other words, the net force must be equal to 0. The second condition is that the clockwise torques must be equal to the counterclockwise torques, which means the net torque must be 0. These are the two conditions. So as an example, if you have two forces, F1 acting here and F2 acting at that point C, and look at that, F1 is acting down, F2 is acting up. And when you consider the torque about the point A, so we are imagining that the pivot is at A, F2 is trying to rotate it counterclockwise, while F1 is trying to rotate it clockwise. And therefore, F1 times AB F1 times AB should be equal to F2 times AC. There it is. F1 times AB should be equal to F2 times AC. And also, F1 is equal to F2. So those are the two conditions. Here, the total net force is 0. Here, the net torque is 0. Let's see how that is applied in problem number 2. So in this question, an object is supported at its ends. If the reaction at one end is 300 Newton, how far from that end is the center of mass? The object has a length of 3 meters and a mass of 100 kilograms. So you have something like a rod supported at its two ends. The length is 3.0 meter and its mass is 100 kilograms. We're given the reaction at one end, but we do not know the reaction at the other end. And we have to find where the center of mass is. Let's do it. A diagram is very important. So here you have the two supports and the two reactions. 300 Newton there, and we do not know the reaction at the other end. So this is the center of mass. We don't know where it is, but we know the weight is 100 times 9.8, which is 9,800 newtons. So everything has got to be in newtons, okay? You can't have newtons and kilograms. So you have to have everything either in newtons or in kilograms. And then we apply the two conditions for static equilibrium. The first one is that the total up forces is equal to the down. So 300 plus N2 should be equal to 9,800. And that will give N2 as 9,500. N2 would be 9,500. And we assume that the distance of the center of mass from the left end is x. So we're looking for the value of x. And we will calculate the torque at this point. We will calculate the torque here. What's the advantage of calculating the torque at that point? The torque due to 9,800 Newton at that point is 0. Because the force is acting right there, there is no distance, and therefore the torque is 0. Remember, torque is force times the perpendicular distance. That means you're going to have one counterclockwise torque, which is by N2, and one clockwise torque, which is by the 300 newtons. So 300 multiplied by x should be equal to N2 multiplied by 3 minus x, right? Because the total distance is 3, and this must be 3 minus x. So when you do all those calculations, here it is. 300 times x is equal to N2 times 3 minus x. You have to distribute this, and N2 is 9,500. And so when you do all those calculations carefully and take a few minutes to look at that, you would get x as 2.91 meter, which means my diagram was completely wrong, because then the center of mass had to be somewhere here, you see. So I was not really thinking about the question when I set it up. There's nothing wrong in what I did, but once you get the answer, you see the total length is 3 meters, so 2.91 should be somewhere here. That's because I took this reaction to be really small, 300 newtons. But I hope you understood that. Let's move on according to this. Okay. The third concept we're going to look at is impulse. There are two ways of defining impulse. Impulse is either the product of force and the time for which it acts. That's one way of defining impulse. Or impulse is the change in momentum. So impulse is either the product of force and the time, or it is the change in momentum. Now that would be well illustrated in this question that I'm going to give you. All right. So in this question that is given, we have a force acting, a force of 10 Newton acts for 5 seconds. 10 Newton acts for 5 seconds on an object of mass 2 kilogram. And that object is initially at rest. So there are two parts. Number one, or A, find the impulse. And B, find the final velocity of the object. Because when a force acts on an object, it's going to move if it was at rest. And so we got to find the final velocity. So a force of 10 Newton acts for 5 seconds. Find the impulse. That is quite simple. Just multiply 10 and 5. Because impulse is the product of force and time. Okay? So that gives 50 Newton second. And then we also know that impulse is change in momentum, don't we? And we already got the impulse, so we can say 50 is equal to change in momentum. Remember, momentum is the product of mass and velocity. So when you say change in momentum, you're going final momentum minus the initial momentum. But what is the initial momentum? The initial momentum is 0 because the object was at rest. So that's why this term became 0. And then it's quite simple. We see that the final velocity is 25 meter per second. Is that? I hope that you got it. Okay, that's how simple it is. Now, I'm giving another part of this, which is important. Where I'm trying to show you that if an object is initially moving along the east or to the east, okay, at 15 meters per second, and then you apply a force on it to the west. So it's moving that way, but you apply a force onto the west, and then it's going to turn around and move to the west. And when you're asked to calculate the change in velocity or even the change in momentum, you should remember to take one as positive while the other is negative. So don't just look at the numbers. The first one is plus 15 and the next one is negative 10. See the force acting? So when you're asked to find the change, it's actually going to be 25. The change in velocity is 25 meters per second. Why? Because it's 15 minus 10. Two negatives make a positive, so 15 plus 10, 25. Well, what if it is the momentum? Same thing. So then you would be asked to find the force. Okay, so let's imagine that the force is acting for 10 seconds. I'm just making up numbers. The force is acting on this object for 10 seconds, right? And we know that there are two ways of calculating the impulse. I've put both together. Product of force and time is equal to the change in momentum. I put both together. And then if I had given you the momentum initially, I'm going to change the units, just the units. I'm going to say, all right, okay, so I'm now making this momentum. The initial momentum was 15 kilogram meter per second, and the final was 10 kilogram meter per second, but to the west. So that's momentum. So now what I can do is, I can just take the change in momentum. See, I got stuck here because I was not given the mass. So that's why I went ahead and changed it to momentum. So now it's easy. I can go minus 10, minus 15. See, I can take it as minus 10, minus 15, which gives you minus 25. So, or you could have gone 15 minus of minus 10, which is plus 25. In either case, the number that you get is 25, not 5, which is what students normally do. It's not 15 minus 10. It's actually 15 plus 10. So, since product of force and time is equal to the change, the right side I get negative 25. On the left side, I have F times 10. So that means divide both sides by 10. And I would get negative 2.5 Newton as the force acting. And the negative here just shows the force was against the motion of the object. The object was going to the east, and the force was against it. So that's why we got a negative. Hope you understood that. So that clearly shows how you could apply the two formulae for impulse. The left side, you have product of force and time. On the right side, you have the change in momentum. But please remember to look at the direction when you take the difference on the right side. Okay? Number 4, rotational inertia or moment of inertia. The definition for moment of inertia of a particle is simply mr squared, mass multiplied by the square of the distance of the particle from the axis. And that is only for a particle. And angular momentum is I times omega. That means it's the product of the rotational inertia and the angular velocity. Also, according to the conservation of angular momentum, I1 omega 1 is equal to I2 omega 2. Remember, this is just a review, that's why I'm going fast. So which means if the angular momentum decreases, the angular velocity increases. Remember the person standing on a rotating platform with hands spread, legs spread out. And if the person suddenly pulls the hands, drops the hands to the body, pulls the feet together, the rotational inertia of the system decreases. And therefore, the angular velocity would increase. Means he would begin spinning faster. Excuse me. So he would begin spinning faster, he or she in that case. Okay. So we will look at this problem. So here we have a disk spinning about an axis passing through its center, and the moment of inertia of the disk is given as 0.2 kilogram meter squared. Okay? So that is given. You need not calculate it, that is given. But now you have a bug, quite a big one, that flies and comes and sits right there on the disk as it is spinning. It's right there. Okay, so the mass of the bug is 0.1 kilogram and it's situated 20 centimeters from the axis. So initially, the disk was spinning at 10 RPM, which is 10 rotations per minute. That's before the bug came and sat on. Now, when the bug sits on the disk, surely the rotational inertia has gone up, so the angular velocity will go down. It'll spin a little slower. So that's what we're trying to find. We're trying to find the new angular velocity. Okay, remember that what is given here is the frequency, and it should actually be in rotations per second. But if we don't change it in this case, it's okay because you will get the answer also in rotations per minute. Anyway, so the moment of inertia of the bug is given by mr squared because the bug is treated as a particle. The mass must be in kilograms, it is, but the distance is in centimeters. So we got to change it in a meter. So 20 divided by 100, 0.2 squared, and when you do that, you get 0.004 kilogram meter squared as the rotational inertia of the bug alone. But now we got to get the total rotational inertia of the disk and the bug. So you add both of them. Okay, that will be the final one. Now this is the angular conservation of angular momentum. I1 omega 1 is equal to I2 omega 2. And so I1 is the rotational inertia of the disk alone, and I2 is the rotational inertia of the disk plus the rotational inertia of the bug, which is here. The disk has a rotational inertia of 0.2, which is given there. So 0.2 plus 0.004, which gives 0.204 kilogram meter squared. So then we use the conservation of angular momentum. So I1 omega 1. Now omega is 2 pi by frequency. 2 pi by frequency. So again, so it's 2 pi by 10 is equal to the new rotational inertia times 2 pi by f. We don't know F. That's what we're trying to find. Again, remember, since you have this in rotations per minute, you're going to get this also in rotations per minute. The 2 pi's are going to cancel off. And then the little algebra, the calculation there will give you the value of the frequency. So frequency is going to be 0.204 divided by 0.02, which is 1.02 rotations per minute. So it did slow down a lot. It was making 10 rotations per minute, but this bug, the heavy one, really slowed it down to 1.02 rotations per minute. This is an important question, demonstrating the application of conservation of angular momentum. Shall we move on to the next one? So the next problem deals with Archimedes principle, which is the law of flotation. Okay? So according to the law of flotation, if an object floats, then the mass of the floating object should be equal to the mass of liquid displaced. So you can also say the weight of the floating object is equal to the weight of liquid displaced. Both are okay, because when you say weight, there's g, acceleration due to gravity on both sides, which gets cancelled. So we'll go with mass of the floating object here is equal to the mass of the liquid displaced by the object. So what do you mean by mass of liquid displaced? When you put an object in the liquid, you see that a certain part of this object will be submerged. And so the volume, the liquid will go up. So that's what you mean by displaced. So whatever is the volume of the object under the liquid, that would be exactly the same as the volume of liquid displaced. So we always got to look at what part of the volume of the solid is under the liquid. That will be the volume of liquid displaced. And that will be shown in this problem. This is a pretty large iceberg, and its area is given. And you can see that it is this part, you can see it as I'm drawing it, that is the water level. So this part is underwater. And that height is given as 90 centimeters. So 90 centimeters of this iceberg is underwater. Its area is 10 meters squared. That's the area of the top face here. That's 10 meters squared. 90 centimeters of the iceberg is underwater. Okay? Now the mass of the iceberg is what we have to find. So how do you find the mass of the iceberg? Just apply Archimedes principle. The mass of the iceberg must be equal to the mass of water displaced by it. Right? Mass of the floating object is equal to the mass of liquid displaced by it. So here we're looking for the mass of the iceberg. That should be equal to the mass of water displaced. So on the left-hand side, we do not know. Let's put it as m. So m, which is the mass of the iceberg, is equal to mass of liquid or mass of water displaced. How do you find mass? Mass is volume multiplied by density. So the volume of water displaced multiplied by the density of water. We know the density of water is 1,000 kilogram per meter cube. We know that. And how do you find the volume? Volume is area times height. So in this case, the area is 10 meters squared and the height is 0.9 meter. We got to have it in meters. And then the density is 1,000 kilogram per meter cube. So when you multiply all those three numbers, you would get the mass of the iceberg as 9,000 kilograms. So that's the mass. It's a big one. That's the mass of the iceberg. So that is an application of Archimedes principle, showing the law of flotation. So here's another one. So you have an object here, cylindrical, and the base is of radius 10 centimeter. The mass of this object is 10 kilogram. Okay? And we have to find the pressure exerted by this object. Now, what is pressure? Pressure is force by area. In this case, force is the weight of this object, isn't it? Force is the weight, and it's acting over that circular area at the base. So we got to find the area of the base and divide the weight by the area. So pressure is force by area, force is mg divided by area. And the area of a circle is pi r squared. We've used it so many times. So mg by pi r squared. M is 10, 9 times 9.8 by pi times, the radius has to be in meter. So it's 0.1 squared. When you do that, you get the pressure as 3121 pascals. Newton per meter squared or pascals or Pascal, either way, okay? So that's how you calculate the pressure. Now, I also want to say that you do not calculate the area all the time using pi r squared. No, you don't do that blindly. If the base has a rectangular shape as shown here, then you calculate the area by multiplying the length with the width. So read the question. If it's a circular base, use pi r squared. If it's a rectangular base, use length times width or length times breadth. Okay, so be smart when you read the problem and look at it carefully and do it. So the next one is flow of liquids. So you have water flowing through a tube, and the velocity of flow is 10 meters per second. 10 meters per second. And if you're asked to find how much water flows per second, that means you will have to find the quantity of water, the volume of water flowing out per second. If you're given the velocity, and if you know the area of cross-section, you just multiply the area of cross-section with the velocity, you will get the rate of flow. You will get how many meter cubes of water is flowing per second. So here the radius is 10 centimeter. The radius is given. So once again, you have to find the area using pi r squared. How do we get the volume rate of flow? The volume rate of flow is area of cross-section multiplied by the velocity. Area is pi r squared. Velocity is given. So 3.14 times, again the radius is in centimeters, so 0.1 squared times 10. And you get the rate of flow as 0.314 meter cube per second. Make sense? And what if this big tube was connected to a smaller tube? So let me make an adjustment there, and so we can do this as another question. So let me get that out, and let's say that this is connected to a smaller tube. And now you are asked to find the velocity of flow in the smaller tube, given the radius of that small part is 3 centimeters. What are you going to do now? Well, we have to remember that the rate of flow through the big one and through the small one are equal. So the volume that flows per second is the same, because water doesn't stagnate inside. So that is the idea. So let's do that. So we know that the volume rate of flow through the small one should also be 0.314. And we also know the volume rate of flow is area times velocity. That will do it. So you see I found the area of cross-section. That is the 3 centimeter in meters. Times the velocity should give the same volume rate of flow. What remains is the math. And when you do that, you are going to get the velocity of flow through the smaller part. Of course, it should flow much faster. Let's see what we get. Remember that in the bigger one, it was flowing at 10 meters per second. But look at that. In the smaller one, it's flowing at 111.11 meter per second. where the area becomes smaller, the speed of flow becomes bigger. So that is how we work out this problem. All right. Now back to rotational motion. So here is the disk rotating at 60 RPM, and then the disk is stopped in 2 minutes. So that means the disk is stopped by applying a gradual torque or force for in 2 minutes. It's just like switching off the ceiling fan. You switch off the ceiling fan, it takes some more time for it to absolutely come to a stop. So that's the kind of thing. Okay. So it's spinning at 60 RPM. It had stopped in 2 minutes. What is the acceleration? So here I'm asking you for the angular acceleration, alpha. Okay. So then you go to what's the initial angular velocity. Remember that angular velocity is 2 pi times f. And f must be in rotations per second. Okay. So 60 RPM divided by 60, because rotations per minute changed into rotations per second. That would give you 6.28 radians per second. That is the initial angular velocity. What about the final angular velocity? Of course, it is 0, because this thing stopped. And to find the angular acceleration, you go alpha is omega f minus omega I by t, because acceleration is a change in angular velocity divided by time. So all you do, 0 minus 6.28 by 120, because it took 2 minutes. 2 minutes is 120 seconds. And you get alpha. Right? Isn't it easy? It is. If you know what you're doing, it's easy. And then I'm going to add another part. I want you to find how many revolutions it made before it came to a stop. So when you first switched it off, from the switching off to when it comes to a stop, it made a certain number of rotations or revolutions, didn't it? So how many times did it rotate before it came to a stop? So we're looking for a number of rotations. To do that, first we find the total angle it made. You know that one rotation is 2 pi radians. So if you could get the angle, you just have to divide that by 2 pi, you would get the total number of rotations. Okay, so let's use kinematics and find the angle. To find the angle, we use this formula, omega it plus 1/2 alpha t squared. So omega I, we already know that. So omega I is 6.28, then time is 120 seconds plus half times. The alpha that we got is negative, remember that? So negative 0.0052120 squared. I hope you can see that. And work that out carefully. You get 753.6 for the first one and minus 374.4, which gives you 379.2 radians. So that gives you the total angle. That gives you the total angle. And then if you want to find the total number of rotations it makes before it stops, just like I told you, divide that by 2 pi, because each rotation is 2 pi radians. So how many revolutions did it make? Total angle was 379.2. Divide that by 2 pi, work it out, and you would get the result. Okay. 2 pi is 6.28, so that gives 60.38 rotations or revolutions. That's all I had. So these are some of the more important questions for exam number 3. You cannot cram these. You got to look at the ideas in each. That means you got to take a few minutes to understand each question. That's the only way you can get it, because the exam questions may not be exactly the same. They will lead to the same concepts or built on the same concepts, but you got to understand. So wish you all the best and see you on the next video.